Hello everyone, welcome to the video lecture of this course finite element method. So this is the third module that we will start discussing today. So this module basically deals with the two-dimensional scalar variable problems. So earlier in the first module we have discussed the concept of the finite element method, then what is discretization, then the concept of the nodes, elements, then the main basic steps of this finite element method, which are pre-processing, then analysis or solver, and the post-processing part. So those general steps of the finite element method we have discussed in details, and different numericals based on the weighted residual method, Galerkin method, Rayleigh-Ritz method, all these things we have discussed in the first module. After that, in the second module, which is basically the one-dimensional problems, there we have discussed the different concept of the shape function and stiffness matrix. Now there the finite element equation for the shape function and the nodal displacements we have seen, and based on those formula we have discussed different complicated numericals for the one-dimensional bar elements. There we have seen how to find the stiffness matrix, then the reaction forces, strain energy, and how to validate or verify the result of the reactions comparing with the applied forces. Those things also we have discussed while discussing the different numericals. Then we have taken into consideration the temperature effect, and based on that concept we have determined the thermal stress for these bar elements, and for spring elements also we have discussed different numericals for their finite element equation. Now today we will discuss the two-dimensional scalar variable problems, and here we will discuss the finite element modeling, and then we will discuss the difference and the concept in between the CST and LST element. Okay, so let us start this lecture. So actually this chapter deals with this module deals with the two-dimensional problems, basically scalar variable problems. These two-dimensional elements, these are actually defined by three or more nodes in a two-dimensional plane, that is a XY plane. Now, the basic element useful for two-dimensional analysis, it is a triangular element. The simplest two-dimensional elements, these are having corner nodes, which we can see in the diagram. It is in figure 3.1. The two-dimensional elements like the triangle, rectangle, quadrilateral, parallelogram, these are shown here. So the triangular element is the basic element which is useful for the two-dimensional analysis. Now a quadrilateral, which you can see in the figure 3.2, it is an assemblage of two or four triangular element. So it is actually obtained by assembling two or four triangular elements. So these are often used to model a wide range of engineering problems actually. Now the two-dimensional finite element formulation actually follows the same steps which is used in the one-dimensional problems. The displacements and distributed body force values are functions of the position indicated by xy. The displacement vector u is given by u equals to a column matrix of u and v, where u and v are the x and y components of u respectively. Now the stresses and strains in this case can be mathematically represented as sigma equals to a column matrix of sigma x, sigma y, and tau xy. And the strain, it can be represented as a column matrix of ex, ey, and gamma xy, where sigma is the normal stress, tau is the shear stress, E is normal strain, and gamma is the shear strain. The concept of the body force we have seen earlier in the one-dimensional problem. So the body force matrix, it can be written or it can be represented as a column matrix of fx fy. Now let us discuss the plane stress and plane strain concept. Actually, this two-dimensional element is extremely important for the plane stress analysis and plane strain analysis. So what happens in case of this plane stress analysis? Actually, such plane stress analysis, it is actually defined to be a state or stress in which the normal stress sigma and the shear stress tau is directed perpendicular to the plane are assumed to be zero. This is the concept of the plane stress. It is actually defined to be a state of stress in which the normal stress and the shear stress directed perpendicular to the plane are assumed to be zero. So generally members that are thin, that means those with a small z dimension compared to the in-plane x and y dimensions, and whose loads act only in the xy plane, can be considered to be under plane stress. Now plates with holes and plates with fillets, these are coming under plane stress analysis problems. So in this figure 3.4 you can see that the plane stress problem, that means a plate with hole and plate with fillet, those examples are shown with diagram. Here T is the surface traction, that is pressure acting on the surface edge or face of a member. It is unit force per area, which is Newton per meter square. The normal stress sigma z, this is 0, and the shear stresses tau xz and tau yz, this is equals to 0. So this is the concept of this plane stress analysis. Next we will discuss the plane strain analysis actually. So it is defined to be a state of strain in which the strain normal to the xy plane and the shear strains are assumed to be 0. So the dams and pipes subjected to loads that remain constant over their lengths are coming under plane strain analysis problems. So here in figure 3.5 you can see that plane strain problems examples are given. So the first example is when a dam is subjected to horizontal loading, and the second example is a pipe subjected to a vertical load. Now here the normal strain Ez, this is 0, and the shear strains, it will be shear strain, actually shear strains gamma xz and gamma yz, this is 0. Next we will discuss the finite element modeling. So this concept of the finite element modeling for one-dimensional problem we have already discussed. Now today we'll discuss the finite element modeling for two-dimensional problem. So the first point is the discretization of structure. So the concept of discretization we have discussed earlier very clearly. So what is that actually? This discretization, it is the art of subdividing a structure into a convenient number of smaller components. So what happens actually, suppose a complex shape or a complex structure is given whose numerical simulation we need to find depending on the boundary condition or mathematical modeling. So what we do after drawing or after the geometrical modeling in the software, we don't simulate that complex shape structure into one go. We actually subdivide or subdivide that part, or that actual structure is actually breaks down into several smaller number of elements. Now those elements are also connected with the nodes. So After that, for each and every element, the numerical simulation is performed and those are assembled finally to get the final solution of that structure. Now, such type of concept or this art of subdividing a structure into a convenient number of smaller components, it is known as the discretization or meshing. In case of the two-dimensional problems, three kinds of finite elements are used. They are triangular element, rectangular element, and a quadrilateral element. Now, in case of truss, the above three elements, these are physically present, but in a continuum, the above three elements exist only in our imagination. So, this next page in the diagram, you can see a continuum. It is shown in figure 3.6 and figure 3.7. That continuum, it is subdivided into eight numbers of elements which are connected to each other with the help of nodes. So this thing is actually written here. The continuum is discretized into 8 triangular elements. The points where the corners of the triangles meet are called nodes, and each triangle formed by 3 nodes and 3 sides is called an element. So here in the figure 3.7 you can see that continuum, it is discretized into 8 triangular elements. For each and every triangle we are having 3 sides and 3 nodes, like for the element 1. So it is having 3 nodes which are 1, 2 and 3. Now here the numbers which are within the circle, these denote the element, and the numbers except the circle or excluding the circle, these are the nodes. So for element 1 you can see the nodes are 1, 2 and 3. Then for element 2 the nodes are 2, 3 and 4. Then for element 3 the nodes are 3, 4 and 5 and so on. Now here the element numbers, these are actually circled to distinguish from the node numbers. The cross section area, then the traction force and body force are constant within each element. But these differ in magnitude from element to element. So better results are obtained by increasing the number of the elements. So if we increase the number of the elements, so that means the discretization or the meshing of the actual structure, it will be more dense. So that means the result or the final result will be more accurate. And figure 3.7 you can see that the triangular elements fill the entire region except a small region at the boundary. So this unfilled region can be eliminated by choosing smaller elements or elements with curved boundaries. Next we are having the second point of the finite element modeling, which is the numbering of nodes. In case of one-dimensional problem, each node is allowed to move only in plus minus x direction, as we have discussed earlier. But in two-dimensional problem, each node is permitted to move in the two directions, that is x and y. So that means each node has 2 degrees of freedom or the nodal displacements. Now, a 3-node finite element model is shown in this diagram figure 3.8. A triangular element is shown which is having 6 degrees of freedom. So in this triangular element, it is having 3 nodes, and for each and every node it is having 2 nodal displacements in x and y direction. Like for the node 2, it is written u2 and v2, that two nodal displacements. So this u2 it is in the x direction and v2 is in the y direction. So in the similar manner, for each and every node, those nodes are having 2 degrees of freedom or 2 nodal displacements for each of them. Now the element connectivity table, it is given here in the right hand side of this slide. heading 1 and 2, they actually refer to the local node numbers of an element, and the corresponding node number on the body are called global numbers. The connectivity this establishes the local global correspondence. Next, we will discuss the concept of the CST, that is the constant strain triangular element. In short, it is written as CST, constant strain triangular element. So what is this? Actually a three-noded triangular element, which you can see in this diagram. So similar kind of three-noded triangular element, it is known as constant strain triangular element. So here you can see for each and every node it is having two nodal displacement or 2 degrees of freedom. So for total 3 nodes, 6 degrees of freedom or 6 nodal displacement we are having here, which are U1, V1, U2, V2 and U3, V3. The element is called constant strain triangular element because it has a constant strain throughout it. So this is the concept of this CST element. Next we will discuss the LST concept. It is the linear strain triangular element. So a 6-noded triangular element, it is known as the linear strain triangular element, which you can see in this diagram. This triangle is having 6 nodes. So corresponding to the 6 node, it is having total 12 nodal displacements or total 12 degrees of freedom. So the displacement functions of the element are quadratic instead of linear, as in the CST. The procedures for development of the stiffness matrix equation for the LST element follow the same steps as those used for the CST element, but the number of equations used for developing the stiffness matrix equation is 12 instead of 6. It is actually a tedious process or a complex process to solve those equations, so we will use a computer to solve many of the mathematical equations. So this is the concept of this LST and CST method. Now there is a comparison in between these two. So this LST element, it is actually preferred than the CST element for plane stress applications when relatively small numbers of nodes are used. So this is like one advantage of LST element. So it is preferred than the CST element for plane stress application when relatively small number of nodes are used. But this LST element is not preferred when large number of nodes are used because the cost of formation of the element stiffness in the equation bandwidth, these are actually high compared to the CST element. And the computer modeling for large number of nodes, these are also difficult for LST element. So this is the comparison in between this CST and LST element. Now we will have some formula based on the CST and LST concept, and based on this formula we will discuss some numericals in the next lectures. So today we will solve one numerical, we will discuss one numerical based on the first formula. So total 12 number of formulas are here. Now for constant strain triangle or CST element, the formula for or the relation in between the shape functions, that is n1 plus n2 plus n3, this is equals to 1. And the coordinate for x is equals to n1 x1 plus n2 x2 plus n3 x3. The coordinate for y is equals to n1 y1 plus n2 y2 plus n3 y3. Or there is another representation to find the coordinate x. This is equals to x1 minus x3 into n1 plus x2 minus x3 into n2 plus x3. And similarly for y, this is y1 minus y3 into n1 plus y2 minus y3 into n2 plus y3. Next, the second formula, it is to find the area of the triangular element. So the area of the triangular element A equals to half multiplied by a 3 by 3 matrix. Next, the third formula, it is a strain displacement matrix for CST element. The P matrix equals to 1 by 2 IC multiplied by a 5 by 3 matrix. So here Q1 equals to y2 minus y3, Q2 equals to y3 minus y1, and Q3 equals to y1 minus y2. And R1 equals to x3 minus x2, R2 equals to x1 minus x3, and R3 equals to x2 minus x1. So this is the formula for the strain displacement matrix for CST element. Next formula, it is basically for stress strain relationship matrix for plane stress problem. So the D matrix equals to E by 1 minus nu square multiplied by 3 by 3 matrix, and E equals to Poisson's ratio, and E equals to Young's modulus. Next, number 5, stress strain relationship matrix for plane strain problem. So the T matrix, it can be represented like this for the stress strain relationship matrix in case of the plane strain problem. Next, we are having the number 6 equation, which is the element stiffness matrix for CST element. The formula for the element stiffness matrix K equals to B matrix transpose multiplied by D multiplied by again B matrix into AT. So this is the formula for the element stiffness matrix for CST element. Next, we are having the formula for element stress sigma equals to T matrix by B matrix by U. And here this sigma matrix, it can be written as sigma x, sigma y, and tau xy on column matrix. So this is equals to D into B multiplied by a column matrix of the nodal displacements. So here sigma x, sigma y, these are the normal stresses. Tau xy, this is the shear stress, and U and B, these are the nodal displacements. Next, the formula for maximum normal stress sigma max, this is written here. So sigma max equals to sigma 1, this is sigma x plus sigma y divided by 2 plus root under sigma x minus sigma y by 2 whole square plus tau xy square. Next formula is for minimum normal stress, that is sigma mean, this is equals to sigma 2, and the formula is written here. Next, for principal angle tan 2 theta sub x p, is equals to 2 tau xy divided by sigma x minus sigma y. Next formula for number 10, this is for element strain. So E matrix is equals to B matrix into U, and this U can be represented in terms of the nodal displacement, it is a column matrix. Next formula is considering the temperature effect. So initial strain E naught. So for plane stress problems, we are having a column matrix of alpha delta T, and 0. Next, initial strain E naught, this is for plane strain problem. So on plus nu multiplied by column matrix, where alpha is coefficient of thermal expansion and nu is the Poisson's ratio. And finally, in point 12, we are having the element temperature force F. This is equals to B matrix transpose multiplied by D matrix multiplied by the E naught matrix into dA. So these are the 12 different numericals, 12 different formulas actually, which we need to implement to solve different problems that we will discuss. Now there is a diagram given. In this diagram we can see that one triangular element is given, and for its 3 nodes the coordinate is given. And within this triangular element one point P is given and whose coordinate is also provided. Now we need to determine the shape functions n1, n2 and n3 at the interior point P for the triangular element. So how to proceed here in this numerical? First we will write all the coordinates which are given here. So corresponding to node 1, if we consider x1 and y1, then x1 is 2, y1 is 3. Corresponding to node 2, x2 is 7, y2 is 4. Corresponding to node 3, x3 is 4, y3 is 7. And the coordinate of P, these are x equals to 3.5 and y equals to 5. We need to find the shape functions n1, n2 and n3 at the interior point P. So for that we need to go back to the earlier formula. So here you can see that the first formula is there where we are having the relations in between the shape functions. So the relation among the shape function is like that n1 plus n2 plus n3, this is equals to 1. Now to find the coordinate, to use the value of the coordinate, we can use the formula which are given here. So we can use this formula, that is x equals to x1 minus x3 into n1 plus x2 minus x3 into n2 plus x3. So this is equation number 1. And y equals to y1 minus y3 multiplied by n1 plus y2 minus y3 multiplied by n2 plus y3. So this equals to equation number 2. So the coordinates, that is the values of x1, x2, x3, y1, y2, y3 and x and y, these are already given in this numerical, so you can put all those required values in the equations 1 and 2. After that we will be having two equations of n1 and n2. So that means we are having two equations and we are having two variables which we can solve easily. So after performing several steps we can find the value of n1, which we are getting as 0.4166. So if we put this value of n1 in any of the earlier equations, then we'll get the value of n2, which we are getting as 0.111. Now we need to find the value of n3. For that we need to implement that relation, that is n1 plus n2 plus n3, this is equals to 1. As we have found out the value of n1 and n2, so that means n3 will be 1 minus n1 minus n2, so this is 0.4723. So after performing this process, we can write the result as the values of the shape functions at the interior point P. N1 equals to 0.4166, N2 is 0.111 and N3 equals to 0.4723. So this is the concept of the CST and LST element that we have discussed today, and the comparison in between these two different elements. We have also discussed the finite element modeling, considering the discretization and number of nodes for these two-dimensional elements. a two-dimensional problem. After that, we have seen total 12 number of equations, and for this 12 number of equations we will solve different numericals, and among those we have discussed one numerical today in this lecture. So this is the end for this lecture.